So I must say that this work kind of started as a 2-day project and then continue a little bit along, but I'm hoping that in the future I'll be able to dedicate more time to that project. So first I'm going to talk and introduce a little bit of what is extended mathematical programming. Then I'm going to talk about an EMP solver that we coded as a C library. And then basically I started looking at Julia and JuMP to see how I could use this EMP solver from JuMP, because I wanted it to be modeling language agnostic. And so this led me to kind of wonder what would be the right way to model this kind of extended mathematical programs problem in JuMP. So first of all, what is EMP? So EMP is basically a framework to model optimization problems that do not fit in the classical optimization models. And we can do that by using simple annotations. And so EMP first started in GAMS. And so in GAMS, you can have multiplayer problems. So MOPEC, basically so generalized Nash equilibrium with some equilibrium constraint. You can have complementarity problems or variational inequalities, bi-level problems, and also multi-stage stochastic programming, disjunctive programs. So I was more interested in the first 3 items and how to use them from JuMP. So maybe this is a bit overkill for the audience, but why designing a tool? The idea is that we want non-expert to use it and to use it correctly. So that's why it should be kind of straightforward to use, to do the transformation ourselves, provide different schemes or way to solve the problem sometimes. And what is really important when you write a solver, Michael has a lot of experience writing path and now path AVI. So it's important to have the structure of the problem almost passed down to the solver. And yeah, you get no error typo, and it's easy to compare between reformulations if you want to see which one works best. So in terms of Julia, I wrote 2 packages. So the first one, sorry, the name is really bad, but you can see that it's based on Ample NL Writer. So this is your classical LQP or an LP solver for MPB. But it's also able to translate some of the EMP data structure. And the second package is more about modeling. So how can we do equilibrium in JuMP and what I call optimal value functions. And I'm going to describe a little bit what those 2 items are. But what I want to put some emphasis on is that I think I would like really to have a clear separation between the 2 and to try, because I would like to encourage maybe other people to write solver for EMP that are not mine. So that's why I try to kind of have a clear distinction between the 2. So first, maybe just explaining what variational inequalities are. Who heard of variational inequalities before coming to that workshop? Yeah, 4 people. So a VI of the first kind is basically trying to find a point in a feasible set so that this inequality here is respected. So basically, if f is a gradient of a function, or f is basically is a partial derivative of the Lagrangian, or you know that your VI usually stems from an optimization problem. And usually it's a better idea to solve the optimization problem rather than the VI. But there are some instances where your function f doesn't have such properties. And so we have another way to express VIs in this inclusion form here. And for that, I need to introduce what's the normal cone operator here. So if you have a set K, the normal cone operator at the point X is generating by your gradients of your constraints. And so basically, solving a VI is to find a point X in your set so that F is contained, minus F, sorry, is contained in the normal cone. And so the link to complementarity problem is that basically, if your feasible set is a positive Orton, then you have a complementarity problem, where this perpendicular operator is just a shorthand notation for having this equality here. So talking about Nash equilibrium problems. So nowadays, you have less and less monopoly, and you have more and more competition between players. So the idea is, a Nash problem is when we have different players that all have their own objectives, and they want usually to maximize their profit, and they're in competition. And then you may have different other actors, or you may have different constraints in your problem. So the idea is that if you take a classical, so this is the optimization problem for each player. So xi is the decision variable of that player, and x minus I is the decision, all the other variables. And so you always usually have interactions, so that, or coupling between the players in the objective function. However, so if you have a coupling in the constraint, then you have a generalized Nash equilibrium. So as example of complete constraints, you may have shared resources. And so to say that I'm not making this up, yesterday Martin gave me an example. For instance, if you have a river and you have some hydro plants on the river, then the water that your inflow that you get depends on whether someone released, the guy before you released some water or not. And it also could come from strategic decisions. One important point is that you have no hierarchy between players. So basically, it's just a collection of players. Otherwise, you would get an MPEC or an EPEC. And as an example of a VI agent that we usually have from economics is the price is given to you by this kind of complementarity relation. So you always suppose that the supply is greater than demand. And so as a solution, you suppose that supply equal demand, and the price is the multiplier kind of associated to that constraint. So how do you solve or compute a solution to a Nash equilibrium problem? Well, you take the first order optimality condition for each agent, and you're basically going to stack them. And so at the end, you have this kind of compact formulation here. Sorry, it should be an NCP, so X is a simply bounded set, and F is non-monotone. So basically, non-monotone means it's kind of related to non-convex. Basically, if you take the subgradient of a convex problem, you have a monotone operator. And this makes it hard to solve. However, pass or pass AVI can solve many of those instances. The GNEP problems are more challenging, especially when you have non-linear constraints. Then usually we fail to find a solution. So what are objective value functions? So quickly, this is just when in your optimization problem you have this kind of quantity where rho is kind of this value function here. So here we suppose that we have just a linear mapping. So this has been introduced by Arakvin. And so you cannot directly give that to your favorite optimization solver. You need to reformulate it. So some examples, you have all the classical fitting or penalty function, L1, L2, Huber, inch loss. So more interesting maybe for people in this audience, you have the coherent risk measure, can be seen at optimal value functions. So when you have to deal with uncertainty, you need to kind of encode what is your behavior with respect to uncertainty. And so the most common tool that people use is to use this expectation values. That means that you risk neutral. However, in many cases, sorry, I should introduce some of my notation. Sigma here is just a support function. So basically, you're just looking for the soup over your set. Sorry. So it is just this quantity here. And so something that has gained a lot of traction is CVAR, also known as AVAR, or expected shortfall, where you're not interested. You're also kind of risk averse. So you're looking usually at the worst outcomes, and you're trying to use that also as a way to use this to see how to kind of take this into account. Basically, if you go broke, you don't want to lose too much money. And so the nice thing here is that you can also compose risk measures, and this translates into doing the Minkowski sum of sets. So just a short overview of the kind of reformulation you can use. You can either see it as a modification of a Lagrangian and use a kind of Nash equilibrium approach with two agents. You can find a dual problem, or you could see that this optimal value functions or frameworks that we use, it's always kind of the functional conjugate of a function, and so in some cases you can explicitly compute it, and then you can reformulate the problem into a form that you can pass to solvers. So this is how our solver works here in the middle. So we can take input from GAMS or Julia, then we get a model and some EMP infrastructure, then we do the model transformation, usually adding variables, adding a constraint, removing some variables. And then as outputs, right now we can only export to GAMS. I'll talk a little bit more about Julia later. And in GAMS, we have an equilibrium solver. And so in this way, you can, after doing some value propagation, you can get back the solution of your problem in Julia. So now, talking a little bit more about how to model those EMP problems, and especially if we want to go also deal with MPECs, EPECs. So we came up recently with the idea that we want to have a graph representing the problem, where the building blocks are mathematical programs. So mathematical programs, basically those could be a classical minimization problem, or could be a VI. And you have two types of nodes. You have either nodes that are mathematical program, or you have equilibrium nodes that are just a collection of mathematical programs. And so why we want to do that, for instance, in the MOPEC case, a colleague of mine had been working on some diagonalization method or Gauss-Seidel methods to solve them. And so if you keep the structure, if you know that you have your player want to solve this problem, maximize or minimize this objective function, then you can fix the other agent variables, you can pass it to your favorite solver, get back the solution, and iterate over and try to use this iterative method to solve. So to give you a little bit of an idea what you can model, so if you have a minimization agent, then we say that it has in its definition another minimization problem that would give you the bilevel class of problems. Now, if your agent owns or has in its inside is defined to have a VI, or more precisely an NCP, then you can have a mathematical problem with complementarity constraint. If it's a general VI, you would get an MPEC. If it's an equilibrium, you would get an MPEC. And things get more interested when you look at EPECs also, because an EPEC, you could have an equilibrium problem where each agent has as a constraint another equilibrium problem here. So this is fairly new, and if you have some feedback, if you think of some models that could be captured by that, I would be, please come talk to me. I would be interested in this kind of feedback. So just to talk a little bit about the internal. So then right now we have only one JuMP model to store basically all the variables and equations. And then we have a list of mathematical program, list of equilibrium, list of special variable, and I forgot we have the root node of the graph to kind of see how this one is constructed. And then each mathematical program has variable equation indices, complementarity informations. It could have some, if it's a minimization problem, maximization problem, you have this information. And then you have the information what kind of mathematical programs are inside that mathematical program, or if you have equilibrium inside that mathematical program. So just an example to show a little bit. The names are not, I'm not fixed on the name, it could be renamed. So here I define a MOPEC, I have one player, I have the market also. I define an equilibrium problem, which has two players. And then right now I use macros that are very similar to the JuMP macros, but have this argument here, which is a mathematical program, so I can directly assign them to a mathematical program. To define VI pairs, we have this signature here. You have the functional part, and then you have the variable constraints defined in a similar way, and then you just call solve EMP. This will dump all the problems, and then in that case you would end up calling GAMS and get back the result in JuMP. And so just something to bounce on the community to see what you're thinking about. There was this question about whether we want the mathematical program to have their own JuMP model or JuMP object, basically. So you can have basically either a monolithic approach where you have one container for the variable equation, and then basically you have a partition of it, which is contained in each mathematical program. So the main challenge here is how to allow the user to nicely define this partition. And if you use more like a mathematical program-based approach, each one has its own JuMP model, and then the collections plus the graph information gives you the whole problem structure. So then ownership, you know which variable belongs to, or equation belongs to each mathematical program. However, you have some difficulties here. If you want to say that some equations are shared, like for instance, if you have the constraint on a river that many agents have, then you can use some tricks to, you can fix a multiplier associated with that constraint, and then you can reduce the problem size, which sometimes helps, and then you have to ensure the consistency. So this is kind of an open question, so if you have any ideas, I would love to hear. And so, yeah, some future work. We would like to use some kind of add support for automatic or symbolic differentiation so that we can directly call our self-pass and pass AVI to make it a little bit more independent of GAMS. And yeah, I think what would be interesting, but I don't know what the status of it is, being able to call, to use JuMP from C. Because for me, it's a hard constraint that my solver is going to be independent of the modeling language, so I think this would be a great feature to have. Yeah, I'm pretty excited about being able to let the user define some optimal value function. Right now, it's hard-coded, but if the user tells me, oh, this is the problem data, then I can do that. And yet define a nice user interface or API for defining those hierarchical optimization problems. Thank you.